Today we're going to start talking about just part one of the fundamental theorem of calculus. So let's go ahead and jump right in. And the first part of the theorem starts by defining this function I of x as a definite integral from a to x of f of t dt. Well, what's that? So I want us to scroll down to this picture, and I've already done a little extra shading here at the bottom. And so first of all, I want you to notice this is not the usual xy coordinate plane. This is actually, instead of x, the input variable that we're using here is the t variable. So we have t and then y. So this function that's drawn here is the function f of t. And when we talk about, we've developed with our definition of the definite integral in the previous section, that if I'm looking at the definite integral from a to x of the function f of t dt, that by definition is this yellow area under the curve. So this is what I of x is defined to be. So it's the area from a to some ending point x. Maybe x was only going to be from a to this x, or maybe it's a to this x, or to the one that's shown, or to one after it. So the x is actually the variable, the part that's varying with this function. So it's the area from a and then up to some value x. That's how we're defining I of x. All right, so now let's go back up, realize, okay, so that's what we're talking about here in terms of this I of x function. All right, now we're going to take the derivative of both sides. So first of all, let's make this prime, a little bit more significant. When I copy and pasted this little image here from our book, they were a little stingy on the prime. For some reason, it didn't copy through very significantly. So if I take the derivative of the left-hand side as a function of x, that means equivalently I'm taking the derivative of the right-hand side. So d over dx, that's my differential operator with respect to x. Now, the conclusion is we're being told that somehow this is equal to f of x, and that's what we want to somewhat prove. It won't be a real formal proof, but we'll kind of motivate that. But for right now, I just want you to think about what I is. So it's that area under the curve from a to x. And then let's think about, just in practical terms, what a derivative is, I prime. So what I want you to just kind of think about here in terms of I prime is that, let's kind of put in parentheses, we'll just say, let's just sort of note that I prime gives, it's a derivative. So what is a derivative? It's a rate of change. So it's giving us the rate of change, and then what is I describing? It's that area. So it's giving the rate of change of the area that we looked at with respect to x, kind of the end point of that interval. So I prime is giving us the rate of change of that area with respect to x. All right, so let's look at then, in the end, we're going to show that this is equal to essentially the height at the final point. That the rate of change, if I went from, if we just kind of scroll back down here, if I went from, instead of x, let's say, ending here, let's say it had ended there, or let's say it ended here, that the rate of change of this area is going to correspond to what really that final point is. That's kind of where this is going to all end. At the end of the day, that's going to be where we end. But let's develop this a bit. All right, so we have defined this I of x function. So we just said I of x is the definite integral from a to x of f of t dt. Again, in parentheses here, our goal is to justify that I prime is really going to be that the rate of change of the area is going to be the height of the shape at that final point, essentially. So first, again, you're going to need to recopy. For some reason, this was my fault. My typing, I lost my I here. I think it just was a prime. So we're going to take the derivative of both sides. So that's just what we have kind of notationally in the second part here. Now our work begins. So we want to start with our definition of the derivative. So limit as h goes to 0 of I of x plus h minus I of x all over h. so we are going to kind of rewrite this. I'm going to pull this 1 over h out in front here. So this little 1 over h guy. So I'm just going to, instead of dividing by h, I'm just going to multiply what I'm going to replace this with a little 1 over h. So we'll just bring that 1 over h in front. And so now we're going to look at replacing the, let's say this color here. So the I of x plus h is what we're going to put into this part right here. So the definition of I of something, that goes back to our definition for I of x up here. By definition, it is the definite integral from a to x plus h of our function f of t dt. So that's our definition for I of x plus h. All right, so now let's look at then the definition for I of x. So that's what we're going to put right in here. So our definition for I of x is just the definite integral from a to x of f of t dt. All right, well, we have a property of definite integrals which says that so I'm just going to recopy my limit as h goes to 0, 1 over h times definite integral a to x plus h. I'm just recopying this whole first part. Now, if I change on the second integral, if I change my limits of integration from a to x to a, when we reverse the limits of integration, then you get the opposite result. That's something we talked about in the last section. So this minus in front will now change to plus integral from x to a of f of t dt. All right, so, well, what does that do for me? Okay, let's again just kind of rewrite this here for a second. Maybe wouldn't have to rewrite this part, but I'm going to go ahead and do it anyway. So limit as h goes to 0, 1 over h. And addition is certainly commutative, so let me just rewrite this as integral from x to a of f of t dt plus the integral from a to x plus h of f of t dt. So we have another property of integrals here, which is going to say that essentially if the first definite integral ends at a and the second definite integral starts at a, and they're both definite integrals of the same function, that this can be combined. So if I look at, let's say this whole thing right here, this together can be rewritten as our definite integral from x to x plus h of f of t dt. Another property of integrals at play there. All right, so now what we want to think about is this geometric interpretation here of this definite integral from x to x plus h of f of t dt. And so, scroll this up just a little bit here. So what I have over here in dark gray in the original picture, well, that's the definition of a definite integral. It's the area under the curve from x to x plus h. All right, so what I want you to kind of observe here is that area, we could bound that area in between, let's say, the area from the left endpoint. So the area from the rectangle with the left endpoint gives us that overestimate or that circumscribed rectangle. And then let's say I use the area from the right endpoint. So let's say then I did the area using the right endpoint as an estimate. Well, that would give us the inscribed rectangle or a lower estimate. So the actual area has to be bound in between those two values. So if I think about the area of that smaller rectangle in blue, its width is h times its height is f of x plus h. And this is going to be less than or equal to this actual area under the curve, so x to x plus h of, f of, definite integral of f of t dt, which will be less than or equal to, and then the overestimate with the left endpoint, that area, again, base is h times the height, which is f of x. So that has to be true. And now let's say we were to look at this and then divide everything through here, all three sides of this inequality. Suppose that we divided all of that through by h. So what would we then have? So we would now have on the far left, we would have our f of x plus h would be less than or equal to 1 over h times the definite integral from x to x plus h of f of t dt is less than or equal to just f of x. And now if I think about what happens as h goes to 0, so the whole idea here then was to think about what happens as h goes to 0. So now suppose we look at that very fact right here. So now I'm going to just think about here what happens as h goes to 0. So as h goes to 0, f of x plus h is going to go to f of x. And on the far, that's kind of the left side, and on the far right side of my compound inequality, there's not even an h there. So I'm kind of looking at what happens on both ends of this inequality. And so I now have just f of x. And in the middle, I now have as h goes to 0. So I should have maybe used I could have used, instead of just saying as, I could have used my formal limit notation here. And then I'm going to have in the middle my limit as h goes to 0 of my 1 over h definite integral x to x plus h of f of t dt. So I'm thinking about now what I can observe here is that what we have, if we look at, I'm running out of different colors here. So let's say maybe that color right there. And maybe this one. Okay. So now if I was to look at this limit as h goes to 0 of 1 over h, x, definite integral from x to x plus h, so that's this whole portion right here, right? So that's what we now have isolated, is that right here. So by a squeeze theorem type of idea, that tells me that this is going to have to go to f of x, if it's bounded by f of x on both sides. So what we have just shown, kind of our conclusion here, is that capital I prime, so this in words is the rate of change of the area, that original yellow area that we were looking at. So the original yellow area up here, so that area. So the rate of change of the area, we've now shown that this is equal to f of x, and this is, if in words, the height of, I guess I'll just say whatever the shape of this area is at the final point. So that's what we have somewhat derived a little bit, not necessarily a formal proof, but we've kind of derived that. So if you think about maybe like incremental changes in this x, that the rate of change of then this area, this yellow area under the curve, is really going to be changing. If you think about, like, I'm adding on, pretend this gray region was really, really tiny. You know, we want to let h go to 0. So think about this gray rectangle being infinitesimally small. So you're adding on like a tiny little rectangle, and its base would be h times its height is f of x. Well, h is going to 0. So you're basically just adding on this little like f of x, this little height at the final point. And so the rate of change of the area is equal to the height of the shape at the final point. All right, so let's just look at a couple of examples here that just involve only utilizing this first part of the fundamental theorem of calculus, which, by the way, some books, what they call part 1 and part 2, sometimes change. I like this order in this book and calling this and this being part 1. So first of all, again, so let's just kind of rewrite here at the top. The fundamental theorem of calculus, part 1, what was it? Let's just kind of rewrite it here. It was really saying that the derivative with respect to x, that's I prime, of the I of x function, which was the definite integral from a to x of this function f of t dt, is equal to f of x. Okay, so that's what we know. All right, so let's look at some examples here. All right, so number 1, so we just want to find capital F prime of x, where capital F of x is equal to the definite integral from 2 to x of cosine t dt. All right, so capital F prime. All right, well, if they want me, they've given me what f is, and they are telling me then to take the derivative of capital F. This is a function of x, so that means I am taking the derivative with respect to x of my definite integral from 2 to x of cosine of t dt. So this is exactly the structure of our fundamental theorem of calculus part 1 that I have written up above. The cosine of t is your function lowercase f of t. And so what this is going to tell me is I'm going to end up back at f, but it's going to be in terms, lowercase f, but it's going to be in terms of x. So my final answer here is going to be that capital F prime is equal to cosine of x. Okay, so when we talk about the first part of the fundamental theorem, we'll kind of come back to this, and we'll do it in another way to help sort of confirm why this is true, but this is strictly applying the first part of the fundamental theorem of calculus. So what we really kind of have here is that capital F is the antiderivative of lowercase f, which was that cosine function there. All right, so let's look at, oops, I jumped way too far. I did not mean to do that. All right, let's look at another example. So these are kind of just symbolic in a lot of ways, just working more now just with the mechanics of that first part of the fundamental theorem. So you might also hear other instructors refer to this in a way that it's kind of essentially saying that the integral, the definite integral, and the derivative in some ways are undoing each other. They're kind of an inverse operation type of thing, and then we get back to kind of the original function, but in terms of x. So that's kind of another way that you might hear that broke down. Okay, so let's just look at maybe one more here. So again, we're going to find capital F prime of x, where capital F of x is defined to be, and this time we're just going to change this same problem ever so slightly, the integral from 2 to x squared of cosine of t dt. Okay, so initially we start off and we say, okay, you want me to find capital F prime. So that means I'm taking the derivative with respect to x of what f of x is defined to be, which is this definite integral from 2 to x squared of cosine of t dt. Now, what's different about this one is on this particular problem, this upper limit here is now an x squared. It's no longer just a plain old x. And so when you're looking at that upper limit here, I want you to think of that as your inside function. And we're really taking a derivative here. We're taking the derivative of capital F prime. So this is the inside of the function f of x. So if f, capital F up here is a function of x, then this upper limit is where the inside of that function is. And so if that inside is more than just an x, then this is going to mean that we are going to need to apply chain rule. Okay, so we are going to need a chain rule kind of version of this. So yes, it's still applying the first part of the fundamental theorem, but it's going to be with a chain rule. So yes, we're going to end up with, so this was initially our lowercase f of t, and we are going to end up with, so our capital F prime is going to get back to this cosine of, but now the inside is going to be this x squared, and because that is more than just a plain old x, then we are going to have to multiply by the derivative of that inside. So we're going to have to multiply by a 2x here. And so this is just highly symbolic at this point. I mean, it does make sense if capital F is a function of x. Where is the input variable here? It's up in the upper limit. And if that is more than just a plain old x, then since we are taking the derivative, that's what we're doing here, we're taking capital F prime, then we need to apply chain rule. So, I mean, we're definitely doing a chain rule. But again, next time when we come back, we're going to look at the first part of the fundamental theorem of calculus, which will give us another way to go back and kind of re-verify what we just did here. And there'll be kind of some additional steps that maybe will help solidify why this is true here. Okay, so that is our first part of the fundamental theorem of calculus. Next time we'll come back and get to part 2.